This is the correction of the first exam of the Mathematics Refresh course 2017. So the first exercise consists in computing the eigenvalues and eigenvector of a matrix M, which is 3 by 3, 3 lines and 3 columns, and to compute the matrix of eigenvalues, of eigenvectors, and several related questions. Here is the matrix, and we want to compute the eigenvalues and eigenvector. So when we see this matrix, there is a first trick to say that this matrix is upper triangular, which means that, in fact, all the coefficients which are under the first diagonal are 0. When I see this matrix, I know automatically that the eigenvalues are 2, 1, and 3. So we have used the fact that this matrix has a particular shape, but never this is not the general method. So if we want to solve it with the general method, the idea is to consider not matrix M, but a matrix M with where we put these 2, 1 minus lambda, 3 minus lambda. So this is the matrix, which is in fact M minus lambda times the identity. Then here are the eigenvalues lambda that we are looking at, and then we know that lambda is one eigenvalue of M if the determinant of this matrix is 0, which is the determinant of M minus lambda times the identity. So now we just have to compute the determinant of this matrix, and once more this can be computed by several ways. The first method, which is really linked to the trick that we used before, is to see that here we have upper triangular matrix, then the determinant of the matrix is the product of 2 minus lambda by 1 minus lambda by 3 minus lambda. Okay, then in fact we find that the polynomial, so determinant of M minus lambda times the identity, is equal to 2 minus lambda times 1 minus lambda times 3 minus lambda. And we see clearly that the roots are 2, 1, and 3, because this is the roots of the characteristic polynomial. Just another way to compute the determinant of M minus lambda times the identity is to use expansion with respect, for example, to the first column, and then this is equal to 2 minus lambda multiplied by minus 1 at the power 1 plus 1. 1 is the number of the line, first line, and 1 is the number of columns, the second one. So this is just 1, so we can skip, and times the determinant of 1 minus lambda minus 1, 0, 3 minus lambda. Okay, so we see that the determinant of, we have the expansion, we multiply this coefficient here by the determinant of this matrix, and here we have 2 zeros, which means that in the expansion with respect to the first column, we have 2 determinants that are multiplied by 0. So if now we compute the determinant of this matrix, we see that this is 1 minus lambda multiplied by 3 minus lambda minus 0 times minus 1, so this is 0, so it's 1 minus lambda multiplied by 3 minus lambda, and then we obtain the same results. So we have seen here also some simple computation of determinants, and it was also some techniques that you have to know. So let's now consider and find the eigenvalues associated, the eigenvectors associated to eigenvalue lambda equal to 1. So in fact, we are just looking for some vector mx, x, so that mx equal to 1 time, so which is the lambda, so 1 times x. So mx equal to x, and then if I rewrite this in a general form, this is 2 minus 1, so 2 minus 1, minus 1, 0, 0, 1 minus 1, minus 1, 0, 0, and 3 minus 1. Okay, so time x equal to 0. So to obtain this formula, I have my matrix M, which is this part, this is the matrix M times X minus X, which is this minus 1, which is here and here. So if we replace these two by 1 by 1, 0, and 2, and if we rewrite X as X1, X2, X3, we can see that the first equation reads X1 minus X2 equal to 0. The second equation is minus X3 equal 0. And the last one is 2x3 equal 0. So from these two equations, we see that in fact x3 is equal to 0. So my vector x, if I look to the possible vector x, here I have a 0. And then, so with that, we can see that these two equations are in fact the same. So in fact, among the three equations that I have, only two are necessary. This is classical because the determinant of m minus lambda, the identity, is equal to 0. And this is something that usually happens when we compute eigenvalues. So if we look now to the first equation, we see that x2 is equal to x1. So in fact, we have that my vector x is x1, x1, and 0. This means that in fact, here I can rewrite my vector x as x1 multiplied by one vector, which is 1, 1, and 0. So this is a classical properties of eigenvector, which is that in fact we don't have one eigenvector, but we have the eigenvector, in fact, a vector space, and then all the vectors that are multiple of 1, 1, 0 are in fact solution of mx equal to x. You can have a look to the course on eigenvalues and eigenvectors. So in the exercise, I ask to have a vector here with a norm equal to 1 and a first component which is positive. So if we look at that, in fact, we just have that the vector x is equal to x1, x1, 0. I can rewrite it like that. And then the norm of x at the square, let's say for the moment, is equal to x1 squared plus x1 square plus 0 square, which is in fact 0. So this is 2x1 square. So I want that the norm of x being equal to 1, which means that the square of the norm is equal to 1 as well. So this means that in fact, in the possible value, I have that x1 square is equal to 1 over 2, which means that x1 is equal to plus minus 1 over square root of 2. So here I have my value of x1 because I impose that the norm of this vector is equal to 1. If we just plot it, we can see that we are in a situation like that. This line is the line of all the possible x. And in fact, I want just a x which is of norm equal to 1, then I have two solutions here. And the one that I want is the one with a positive first component, which means that in fact I need to put a plus here. So my vector x is equal to 1 over square root of 2, 1 over square root of 2, 0. And then I have the solution and my first eigenvector x associated, or x1, associated to lambda 1 equal to 1. So we can do the same for the other two eigenvalues, and we find the following result, that for lambda equal to 2, then x, or this is lambda 2, x2 is equal to 1, 0, 0, and that for lambda 3 equal to 3, the vector is 1 over square root of 6, 1 over minus 1 over square root of 6, and 2 over square root of 6. And this is x3. So, in fact, if we look, the diagonal matrix lambda of eigenvalues is 1, 0, 0, 0, 2, 0, 0, 0, 3. And the matrix that I call phi is the matrix of 1 over square root of 2, 1 over square root of 2, and 0. The second vector is 1, 0, 0, and then 1 over square root of 6, minus 1 over square root of 6, and 2 over square root of 6. And then we have matrix lambda and phi. So we now want to compute the inverse psi of matrix phi. So psi equal to phi minus 1, which means that when I multiply phi by psi, I obtain the identity. So if we look to the first column of psi, if we rewrite psi like this, so this is a 3 by 3 matrix, I don't know the coefficient, but when I multiply phi by psi, I obtain the identity. So what is here the first column of the identity? This is the multiplication of my matrix phi by the first column of my matrix psi. So if I skip for the moment the two last columns, if I want to find the first column of psi, I just need to solve the linear system phi multiplied by first column of psi equal to 1, 0, 0. So for that, I need to solve a linear system. And when I have the first column, I can find the second column and third column. So we can see here that we can obtain the inverse of a matrix by solving 3 linear systems. So if I want to solve 3 linear systems, the more easy is to solve just a generic linear system like that. So I suppress all of that, oops, like this. Now this is more or less clean. And then, qu'est-ce que ça m'a fait? And then I just look to x1, x2, x3, looking for this vector, which is the solution of 1, 0, 0, 0, 1, 0, and 0, 0, 1. We can write it like y1, y2, y3, so I can solve the 3 linear system in just one generic resolution, and after I will replace y1, y2, y3 by 1, 0, 0, and the adequate value. So if we look to this, we can just see that here there is something very simple, because the last equation is that 2 over square root of 6 times x3 equal to y3, which means that x3 is equal to square root of 6 divided by 2y3. So now I need to find x1 and x2, so I use the second equation. So x1 divided by square root of 2 is equal to y2 plus 1 over square root of 6 times x3. So you see that this x3 goes to the right hand side, and then I can use, because I know x3, which is equal to y3, I use the first equation. So this is y2 plus y3 divided by 2. I can then say that x1 equal to square root of 2 times y2 plus 1 over square root of 2 times y3. So I have the expression for x1. Now I need the expression of x2, and then x2 is equal 2, so I use the first equation, donc y1 minus x1 over square root of 2 minus x3 over square root of 6. So this is y1 minus x1 over square root of 2. So this is minus y2 minus y3 divided by 2 and minus x3 divided by square root of 6. So this is sum over minus my y3 divided by 2. And then this is y1 minus y2 minus y3. And then I have the expression of x2. Now I can determine the expression of psi. So if I want to obtain psi, I just here summarize the formula. And then for the first column, y1 is equal to 1, y2 equal to 0, and y3 equal to 0. So for matrix psi, I have, so first column 0, 1, 0. For the second column, this is 1, 0, 1, 0. So square root of 2 minus 1, 0. And for the third column, this is y3, so 1 over square root of 2 minus 1 and square root of 6 divided by 2. Then I have now the expression of my matrix psi, and we can check, but you can do by yourself, that phi psi equal to I3. So yes, the important thing is that we know that m times phi is equal, so if phi is the matrix of the eigenvector, is equal to phi times the matrix lambda. Just one thing, when we have some vector, we are used to write mx equal to lambda x. So multiplication where lambda is on the left, and for the matrix, as we multiply the column, the lambda is on the right. Then, if we now multiply by the psi matrix, we see that in fact psi m phi equal to psi phi, like this is the identity, times lambda. So here we have the image of m in the matrix phi. For the last question, the only things that we have to see is that m prime is equal to 2 times m. So you can check, but in fact this is in fact just twice the matrix m. So psi times m prime phi is equal to 2 lambda. And then we have the answer to the last question really easily. So let's now consider the second equation. So we have a polynomial which is of order 3, and this polynomial we want to find the roots. So this is the possible x, so if this is p of x, then this is the value x for which p of x equal to 0. So this is a polynomial of degree 3, and then for that we don't have some simple formula, and then the idea is to find some nice possible value for a root for this polynomial. And then we can say that if we add the coefficient of the polynomial, this is 1 plus 2627 plus 2350 minus 50. So this means that for x equal to 1, I have p of x, which is equal to 0. So we have one first root of this polynomial, and which is obtained by just looking at the polynomial. So now we want to find the two other roots of the polynomials, and then first we need to factorize this polynomial, because we know that p of x can be written at x minus 1, so 1 is the root of the polynomial, times another polynomial, which is like ax squared plus bx plus c. So we don't know a, b, and c, but we can expand the first polynomial. So this is a x3 plus bx squared plus cx minus ax squared plus minus bx minus c, and then this is, I now collect all the term plus, so b minus ax squared plus c minus b times x minus c. And then this is p of x, so I can identify the coefficients. So if I identify the coefficient of order of degree 3, then I obtain that, a equal to 1. Then b minus a is equal to 26. So as a is 1, b is equal to 27. C minus b is equal to 23. So I identify this c minus b to 23. Then c is equal to 23 plus b, 23 plus 27, so this is 50. And then here we can check that everything is correct because we have minus 50, which is equal to this minus 50 here. So in fact, we can rewrite that p of x is equal to x minus 1 times x squared plus 27x plus 50. So now I just need to find the roots of this second polynomial that I can call q of x, and then I will have the three roots of my polynomial. So let's now find the root of q of x. So we have several ways to proceed. The first, yes, we can say that the most straightforward, even if there is a trick, is to say that this is x minus a multiplied by x minus b. So a and b are the two roots that I'm looking at, and then this is x squared minus a plus b x plus ab. And then we can see that we have ab equal to 50 and a plus b equal to minus 27. So here we can see that we have one solution, that a equal to minus 2 and b equal to minus 25. So this is a way to find the two roots of the polynomial. Okay, here there is a trick, and from these two equations I can identify my two roots. So we have the classical mean, which is to find the discriminant of the polynomial, which is 27 squared minus 4 times 1 multiplied by 50. So this is equal to 729 minus 200, and then this is 529, and I think that this is clear for everybody that this is 23 square. It's clear for everybody. Perhaps it's a joke, but yes, okay, so we can at least find this. So now I think that a and b are equal to minus 27 plus or minus 23 divided by 2. So minus 27 minus 23, then this is minus 50 divided by 2, so I have a equal to minus 25, and we have that b is equal to, so this is for plus, minus 27 plus 23, this is minus 4 divided by 2, minus 2, and then we obtain a and b as we have seen previously. So the roots of the polynomial, are lambda 1 equal to 1, lambda 2 equal to minus 2, and lambda 3 equal to minus 25. So now we will correct the third exercise. So we have a function f, which is equal to x squared plus 2xy plus y squared. And then we consider the variable change in polar coordinates. So x equal to r cosine theta, y equal r2 sine theta. And then we want to compute the partial derivative of f with respect to r and theta. So for the first method, we just have to replace x and y in the expression of f. So we find that f of r and theta, I put a at here just to say that this is a function with respect to r and theta. So this is x squared. So this is x squared cosine square of theta plus 2. So xy, I still have r squared cosine theta sine theta plus r square sine square of theta. We can see that we have some cosine square plus sine square, so this is r square times 1. I can also factorize by this r square, so 1 plus 2 cosine of theta sine of theta. So now I have the expression of my function f in the polar coordinates, and then if I want to compute the partial derivative with respect to r, this is very simple because in fact here we can see that all this part is a function which doesn't depend on r, so this is assumed to be a constant, and then this is the r square, so this is 2r times 1 plus 2 cosine of theta multiplied by sine of theta. So this is my first partial derivative. And now for the partial derivative with respect to theta, this is now this r square, which is constant, and then I have to derive the function in the bracket. So this 1, when I derive, this is nothing. I have the 2 that can be put in factor, and then I just have to derive with respect to theta the product cosine theta times sine theta. So this is a product. So this is cosine multiplied by the derivative of sine, but the derivative of cosine is cosine itself, so this is a cosine square, and the derivative of cosine, which is minus sine multiplied by sine, so minus sine theta square. So we can see that here this is the partial derivative, and we can rewrite that this is 2r square multiplied by cosine of 2 theta. So here I have computed my two partial derivative with respect to r and theta of my function. So we can refine all this formula by a second mean, which is to write that d of f with respect to r is equal to d of f with respect to x multiplied by d of x with respect to r plus df. So df dy dy dr. And then so df over dx is equal, then we just have to derive this with partial derivative with respect to x. So this is 2x plus 2y. So this is 2 times x plus y. And so this is df over dx. We can see that we can compute exactly the same. So df with respect to dy is equal to 2 times x plus y. So because we have a symmetry in x and y, so we can reobtain that, and dx with respect to dr is just equal to cosine of theta, and dy over dr is equal to sine of theta, which means that df dr is equal to, so I have this df over dx and df over dy, which are equal to 2 times x plus y. So this is 2 times r of cosine of theta plus sine of theta. So this is for this, and I multiply by dx over dr. So this is cosine of theta plus sine of theta. So here I see that this is a perfect square, and then this is equal to 2r times cosine square plus sine square plus 2 cosine theta sine of theta, and this is 1, and then this is equal to 2r times 1 plus 2 cosine theta sine of theta. So for the second derivative, so which is the derivative with respect to theta, I just have to replace that. So this, 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 and if I suppress all of that, okay, theta, theta, theta. So dx over d theta is minus r sine theta, and dy over d theta is r cosine of theta, and then d rho f over d rho theta is 2r times cos theta plus sine theta. So this term here is this plus this, which is the same. Then I have to just to multiply by r. I multiply by cosine of theta minus sine of theta. So we see that here that this is 2r square multiplied by cosine square minus sine square of theta, and this is exactly the expression that we have before. So exercise 4. So now I have a differential equation. My unknown is f. Solution of this equation and two initial conditions. This is second order equation. Then I need two initial conditions, one on f and one on f prime. So if we look at that, we know that f of x is in fact a sum of what we can say a general solution plus a particular solution. This particular solution is one solution of the differential equation, but which is not fulfilling the initial condition. If it fulfills the initial condition, then we have the solution of the equation. So the work is done. Nevertheless, we don't ask to this particular solution to be solution of that with the initial condition. So, and this general solution is the solution of the homogeneous problem, and we can see here that I put a banana skin, which means that this minus 12 is in fact the forcing, and we should put this on the right hand side, because when we look to the differential equation, we just keep the term with f on the left hand side. Okay, so let's find the particular solution. So for this, we can see that the right hand side or the forcing is just this 12, which is now on the right hand side. So what we want to solve is to find some function f, that f second of x minus f prime of x minus 12 f of x is equal to 12. So this is a polynomial, or we can say constant function. And then for that, we don't need to spend too much time, because we have one particular solution, that is that fp is just the function equal to minus 1. Because in fact, fp of e, if we derive this f prime, is 0. And then f second is also 0, and then we have the particular solution fp, which is equal to minus 1. So now if we want to find the general solution, we just have to skip the forcing. So f second of x minus f prime of x minus 12 f of x is equal to 0. So here we see that the 12 has gone to find the general solution, and then for that we looked at function f of x which are under the form e to the px. And then if we follow the theory, we find that p that we are looking at is solution of the characteristic polynomial, which is 1 times p squared minus p minus 12 equals 0. So this is a polynomial that we can solve, and then the solution of this polynomial, if we look to the roots, so to the number for which the polynomial is equal to 0, we can find that the two roots are p equal minus 3 and p equal to 4. Okay, because we have that the product is equal to minus 12 and that the sum or minus the sum is equal to minus 1, then we have the two roots of the polynomial. So we see that the general solution, fg of x, can be written as a times a minus 3 of x plus b e to the 4x. So this is two constants that we don't know, and we will use the initial condition to find these two constants. So now I know that my function f of x can be written as my particular solution, so minus 1 plus e a minus 3x plus b e to the 4x, and that we have that f of 0 is equal to 5 and f prime of 0 equal to 17. So f of 0, this is equal to minus 1 plus a plus b, because when x is equal to 0, exponential e to 0 is 1, and f prime of x is equal to, so minus 1 derivative is 0, so minus 3a minus 3x plus 4b e of 4x, and then f prime of 0 is equal to minus 3a plus 4b. And then this is equal to 5, and this is equal to 17. And then we have two equations and two unknowns and two equations. So we know that a plus b is equal to 6, and minus 3a plus 4b equal to 17. And then we just need to find a and b, so I can multiply this equation by 3 and this one by 1 and make the sum. So I have this 3a minus 3a, this is to 0, 3b plus 4b, this is 7b, which is equal to 6 times 3, 18, plus 17, so this is 35. So 7b equal 35, this means that b equal to 5. And then as I see that b is equal to 5, as a plus b is equal to 6, a equal to 1. So this means that now my function f of x is equal to, and I replace a is equal to 1 and b is equal to 5. And I have the solution of my differential equation. Exercise 5 is an exercise for acoustician. So we have two fields, P and T and V, and this is two harmonic signals, and they are expressed in complex representation. So which means that in fact this P of T, which is equal to a cosine or a P0 times cosine of omega t plus some phase shift, is in fact the real part of a complex amplitude p hat times e to the g omega t. And this is the same for v, and then we know that v of t is the real part of v hat e to the j omega t. And then we want to compute the mean value of v and the mean value of the energy flow, which is the product of p of t times v of t. So for the first question, we want the average of v, which is the integral, so 1 over t times the integral over one period of v of t dt. So this is the mean value of v. So for a first year acoustic student, strictly we know that this is 0 because this is a sinusoidal function on a period, then the value of a sinusoidal function of a period is clearly 0. Of course, we can find it with the expression here, but yes, this is something that that we won't do. More interesting is the second question, which is find the average value of w of t, which is the in fact the integral, so 1 over t times the integral between 0 and t of p of t multiplied by v of t. So we can compute this by several ways, and one thing not to do is just to say that to skip the complex notation, to say that this is z of t times p0 v0 cosine of omega t plus phi or phi p multiplied by cosine of omega t plus phi v dt. Because here we have a product of two trigonometric functions, we can multiply. Of course, there is some formula and we can handle with these two formula, but it is not so simple, especially because we have this two-phase shift here. Okay, so this, I don't want to do this like this. And then we will replace by the complex representation just by saying that in fact here we have 1 over t that will be everywhere times the average between 0 of t times the real part of the j omega t multiplied by the real part of e to the j omega t dt. And then this is the real part, so we can say that this is 1 over t times the integral of p e to the j omega t plus the complex conjugate e minus g omega t over 2 multiplied by v omega t plus the complex conjugate. Okay, so we still have the product, but we see that here we have some product with some exponential function. It's very nice to multiply exponential function, and especially the phase shift also is in the complex amplitude p hat and v hat. And then now I just have to expand, so this is 1 over 4t, so the 4 is 2 by 2, but it's not a dt, it's 2, times the integral between 0 and t of p v e to the 2 j omega t plus p at v. So this e to the g omega t is the product of this multiplied by this. And then now when consider this factor multiplied by this one, we see that this is e to the minus j omega t multiplied by e to the j omega t. And then this is 1, so this is p at v plus p at v at square plus no, not square. This is the complex conjugate. E minus 2 gi omega t dt. And then we see in the integral that we have two terms, this term and this term, that are some trigonometric function of circular frequency 2 omega. And then we can see these two terms are 0. And this is constant. And then we can rewrite that it's very easy. This is 1 over 40 times the constant function multiplied by t. Plus p v star. Okay, so this t can be factorized with this, and here we see that we have a number multiplied and added with its complex conjugate. So now this is 1 over 2 times the real part of p v star. And then we have computed the flow energy. So several remarks. So the first remark is that this number is not 0 except when the product of p v star is purely imaginary, but this is a particular case. Second, this is a formula that we should know by Earth, and then we have seen that it's more easy to use complex number. And the last remark, which is that, okay, p and t, this is two real numbers. So this integral here is real. Of course, this is my real signal, they are real, and then my integral is real. Here, when we look at all this expression, we have complex numbers. So in this complex number, I have a real part and imaginary part. But when we arrive at the end of the calculation, here, you can see that this number is real. This is the identification that I've done here. And of course, the result that I obtain is real. But if I make some mistakes in my calculation, we can see that at the end I don't have a real number. For example, if perhaps I put a minus here because I make some mistake in my calculation, I have here a purely imaginary number, which is not real, so I make a mistake. So this means that it's more simple to use complex number, complex amplitude, because we have exponential. And second, at the end, you should check that your results are at least are correct, and by making some small tests. Exercise 6 is still an exercise of linear algebra, so I have a matrix here, and I want to determine if the matrix with the free vector is a basis of R3, because this is still a 3 by 3 matrix. So to check that if this matrix is a basis, we have several ways. This means that, and the first one perhaps is to compute the determinant of the matrix. So I have computed the determinant. You can do it by yourself, but the determinant of phi is equal to 1. You can compute, and then as this is different from 0, then we know that the free vector constitute a basis of R3. Another way to know if this family of free vector is a basis is to know if they are or not linearly independent. So this means that, in fact, if I find a combination of the free vector, which is with some coefficient or some weight lambda 1, lambda 2, lambda 3, so lambda 1, 1, minus 1, 0, plus lambda 2 times minus 1, 2, minus 1, plus lambda 3 times 0, minus 1, 2. You see that this free vector here correspond to first column, second column, and third column. Then if this combination is equal to 0, okay, so suppose that I have three coefficients, lambda 1, lambda 2, lambda 3, and then the combination is equal to 0. So there is a trivial combination, which is lambda 1 equal lambda 2 equal lambda 3 equal 0. So if lambda 1, lambda 2, lambda 3 are equal to 0, of course, the sum is 0, 0, 0. In fact, this is the 0, 0, 0 vector here, but we used to note it 0. And then, if this is the only possibility, if this is the only one, then in fact, these three vectors constitute a basis. This means, in other way, that we cannot write one vector as a combination of the two over one. Okay, so let's suppose that we have one combination like that. Let's see what are the necessary conditions on lambda 1, lambda 2, lambda 3. So if we look to the first equation, relative to the first row, we have that lambda 1 minus lambda 2 equal to 0, because there is no lambda 3 here. So we have that lambda 1 equal to lambda 2. If we look to the third line, we have that minus lambda 2 plus 2 lambda 3 equal 0, which means that lambda 2 is equal to 2 lambda 3. And then if we look to the last line, we have minus lambda 1 plus 2 lambda 2 minus 1 lambda 3, or minus lambda 3, equals 0. And then we can replace in this equation lambda 1 and lambda 3 by their expression in function of lambda 2. And then we have that minus lambda 2 plus 2 lambda 2 minus lambda 3. So this is minus lambda 2 over 2 equal to 0. And then we have 2 lambda 2 minus lambda 2, this is 1 lambda 2, minus lambda 2 over 2, this is lambda 2 over 2 equal to 0. This means that in fact lambda 2 is equal to 0, lambda 1 equal to 0, and lambda 3 equal to 0. So if we consider the combination of the three vectors with some weights and that this combination is 0, automatically we know that lambda 1, lambda 2, lambda 3 are 0. So this matrix constitutes a basis of R3. And the last question was relative to this matrix. So we know that now these three vectors constitute a basis of R3, but the point is that is this basis orthonormal? So what does it mean, orthonormal? This means that all the column vectors, which are here, so if I call this phi1, phi2, and phi3, this means that the norm of phi1 is equal to the norm of phi2 is equal to the norm of phi3 and is equal to 1. So this means that the three vectors have a norm equal to 1. And the second property for a matrix to be orthogonal is that phi1 is orthogonal to phi2, which means that the inner product of phi1 and phi2 is equal to 0. And the same, phi1 is orthogonal to phi3 and phi2 is orthogonal to phi3. So all the vectors are mutually orthogonal. If I take two vectors, they are orthogonal, and each vector has a norm of 1. So this matrix is clearly not orthogonal for several reasons. If we look just to the norm of phi1, or let's say it's more easy to compute phi1 square than phi1 to skip the square root, and then this is 1 square plus minus 1 square, and then this is equal to 2. Okay, so this means that phi1 is not of norm equal to 1 because the norm of phi1 is equal to square root of 2. So this norm of phi1 is different from 1. So even if all the other properties are necessary, are correct, the fact that the norm of phi1 is different from 1 makes the solution to the matrix not to be orthogonal. So we can see also that the norm of phi2 is not equal to 1 and the norm of phi3 is not equal to 1. So you can compute, I don't do that yet. And just also because we are just, we can also, I can give you some other reason, but if we compute phi1, phi2, then this is equal to 1 multiplied by minus 1 plus minus 1 multiplied by 2 plus 0 multiplied by 1. Okay, so here this is the first component of phi1, second component of phi1, third component of phi1, and the same for phi2. And then if we compute that, we have minus 1, minus 2, plus 0. So this is equal to minus 3, and this is different from 0. So we have that phi1 and phi2 are not mutually orthogonal. So this property is not valid anymore. Okay, so we can see clearly that this matrix is not orthogonal. Just to remind you, because we are in the refresher course, we can also see and gather all these properties which are here. We can gather them by saying that phi, or matrix M, is orthogonal. This is equivalent than M transpose M equal to the identity. In other words, M minus 1, the inverse of M, is equal to its transposed. So this is some matrix for which are very interesting, because one difficult operation with matrix is to compute the inverse, and then if we just have to transpose, this means to swap line and rows and columns. Then to swap these lines and columns or rows and columns, this is something which can be done very easily. So this is the end of the resolution of this exam, and then I hope that you have some additional information, and if you have some more questions, you can send me an SMS, email.